Welcome to the deep dive. Today, we're going to be looking at this really interesting chapter from India's NCERT Class XII Physics textbook.
Hi.
It's called Dual Nature of Radiation and Matter.
Sounds pretty complex.
It is.
Yeah.
But big thanks to NCERT for making this freely available for everybody.
Absolutely.
So get ready to explore the world where light acts like
This is going to be good.
both a wave and a particle.
Okay.
And where everyday objects have a hidden wave-like side.
I love it. All right. So we're going to be diving into some concepts that I think really revolutionized the way that we understand physics back in the early 20th century.
All right. So this chapter kicks off with this phenomenon called cathode rays.
All right.
And that led to the discovery of the electron.
Right.
So just imagine a glass tube, right?
Okay.
And most of the air has been sucked out.
Right.
So it creates this near vacuum.
Okay. Got it.
And when electricity flows through this tube,
Yeah.
scientists observe this mysterious glow.
That's right.
They're like, what's going on?
Exactly.
It turned out this glow was caused by streams of negatively charged particles.
Okay.
They call them cathode rays, right?
Right.
And these particles, well, they ended up being electrons.
Yes.
And electrons are like the
fundamental building blocks of all matter.
Exactly. And through all these experiments with like electric and magnetic field scientists, they figured out how to determine the charge and mass of these electrons.
Yep.
So electrons are those tiny, tiny things whizzing around the nucleus of an atom, right?
That's right, yeah. The discovery and characterization of the electron, I mean,
huge.
That was a major, major step forward in our understanding of atomic structure.
Absolutely.
For sure.
So these electrons, though, they don't always stay trapped inside atoms.
That's right.
The chapter talks about how electrons can be emitted from materials. And this process is called?
Electron emission.
Electron emission.
Yeah.
Okay.
So imagine you've got these electrons.
Okay.
They're kind of held within a metal by this attractive force of the ions.
Okay.
But to break free from the metal to be emitted, they need a certain minimum amount of energy.
They got to get out of there somehow.
Yeah, they got to have enough energy.
Okay.
And we call that minimum energy the work function.
Work function.
Yeah. And you can think about it as kind of like an energy barrier.
Oh, okay.
That the electrons have to overcome.
Okay.
Yeah.
So how do they get this energy? How do electrons get enough energy to escape?
That's a great question.
Do they just like jump out on their own?
No, they need a little help.
A little push.
A little push.
Okay.
There's a few ways we can give electrons this extra energy.
Right.
One way is by heating the metal.
Oh, okay.
Just heat it up.
So like give them thermal nudge.
Yeah, like a thermal nudge.
Out of there.
Exactly.
Oh.
Another way is by applying a strong electric field, which can pull them out like a powerful magnet.
Interesting.
Yeah, and then there's a really intriguing way.
Okay, I'm listening.
And that's shining light on the metal.
Shining light on a metal to release electrons.
Yes.
That sounds almost magical.
It is. It's a fascinating phenomenon called the photoelectric effect.
Okay.
And this effect was one of the key discoveries that led to our understanding of this dual nature of light.
Dual nature, what do you mean by that?
Well, for centuries, scientists believed that light was purely a wave, right?
Okay.
But this photoelectric effect, that really challenged this classical view.
Really? So the photoelectric effect, can you explain like what it is?
Yeah, of course. So imagine you're shining a light on a metal, right?
Okay.
And what scientists observed was that under certain conditions, electrons would be emitted from the metal surface.
Interesting.
So this emission of electrons due to light, that's the photoelectric effect.
Okay, so you shine light on a metal and electrons fly out.
Yeah.
What's so strange about that?
Well, what's strange is that the classical wave theory of light, it just couldn't explain all the observations associated with the photoelectric effect.
Okay, can you give me like an example?
Yeah, sure. One puzzling observation was that there's a specific minimum frequency of light needed for electrons to be emitted at all. We call this the threshold frequency.
Okay.
Below this threshold frequency, no electrons are emitted.
Oh, wow.
No matter how bright or intense the light is.
So you could have a super, super bright light.
Yeah, you could have the brightest light imaginable.
Yeah.
But if the frequency is below that threshold, nothing.
Nothing.
No electrons.
Wow.
And this didn't make sense from the classical wave theory perspective. According to that theory, the energy of light is related to its intensity, right? So you'd think brighter light should be able to eject electrons no matter what.
Yeah, that makes sense.
Regardless of its frequency.
Okay, so if the wave theory couldn't explain it, what did?
Well, in 1905, Albert Einstein.
Of course, Einstein.
Yeah.
Had to be him.
He proposed this revolutionary solution.
Okay.
He suggested that light is not only a wave, but it also behaves like a stream of particles called photons.
Photons? Are those like tiny packets of light?
That's a good way to think about it. Yeah, each photon carries a specific amount of energy. And this energy is related to the photon's frequency.
Okay.
So Einstein's idea was that when a photon hits the metal, it can transfer its energy to an electron.
Okay.
If the photon's energy is equal to or greater than the metal's work function, the electron can absorb enough energy to escape.
Got it.
Yeah.
So if the light's frequency is below the threshold, the photons don't have enough energy to overcome the work function.
Yeah.
And no electrons are emitted.
Exactly.
Interesting.
So Einstein's explanation of the photoelectric effect was a major, major breakthrough.
Yeah.
It introduced this concept of light quanta.
Okay.
This idea that light energy exists in these discrete packets or photons.
Got it.
And this idea, well, it won Einstein the Nobel Prize.
Wow.
And it really revolutionized our understanding of the nature of light.
Einstein really was a genius.
He was ahead of his time.
Yeah. So we've established that light, which, we used to think of as a wave, can also behave as a particle.
Absolutely.
But what about matter? Which we thought was made of particles, right?
Right.
Could matter also have like a wave-like nature?
That is the question.
That is the question.
That a French physicist named Louis de Broglie pondered back in 1924.
All right.
And he made a very bold hypothesis.
Right.
What if matter, like electrons, could also behave like waves?
A wave-like electron. How is that even possible?
I know, right?
How can a particle be a wave?
It is a mind-boggling concept, right?
Yeah.
De Broglie, he proposed that all matter has a wavelength associated with it.
Okay.
And this wavelength, it depends on the matter's momentum.
Momentum. Isn't that just like a measure of how much motion an object has?
Momentum is more precisely defined as the product of an object's mass and its velocity. Okay. So like heavier object moving at the same speed has more momentum than a lighter object.
Makes sense.
And according to de Broglie, the wavelength of a particle is inversely proportional to its momentum.
Okay.
Yeah.
So a tiny electron with its small mass would have a much larger wavelength.
Much larger.
Compared to, say, a baseball.
Yeah.
Even if they were moving at the same speed.
Exactly.
Wow.
De Broglie, he even came up with an equation to calculate this.
The wavelength of a moving particle.
Okay.
It's called the de Broglie wavelength equation.
Got it.
And it states that the wavelength, which we represent with the Greek letter lambda, is equal to Planck's constant, represented by h, divided by the particle's momentum, p.
Okay, so are you saying that even massive objects like planets have a wavelength?
Technically, yes.
Wow.
But the wavelengths associated with these macroscopic objects, like planets, baseballs, even humans, they're so incredibly tiny that they're practically impossible to detect.
They're just so small.
Yeah, that's why we don't observe this wave-like nature of matter in our everyday world.
Got it. So this wave-like behavior of matter is only really relevant in that microscopic world of atoms and subatomic particles.
Precisely.
Okay.
In the realm of atoms and electrons, this wave nature of matter, it has significant consequences.
And this is where the field of quantum mechanics comes in.
Quantum mechanics?
Yeah, quantum mechanics is a branch of physics that describes the behavior of matter at these atomic and subatomic levels.
I've heard of quantum mechanics, but it's always seemed like a very complex and mysterious subject.
It can be. It's a fascinating field, that's for sure.
Yeah.
It can be quite counterintuitive at times.
Yeah.
But at its core, quantum mechanics, it incorporates this wave-particle duality of matter.
Right.
And this duality, it helps explain many phenomena that can't be explained by classical physics.
Can you give me an example of how this wave-particle duality plays out in the quantum world?
Yeah. One example is the behavior of electrons in atoms.
Okay.
So, according to classical physics, Electrons that are orbiting the nucleus
Yeah.
should constantly emit radiation and lose energy, and eventually they should spiral into the nucleus.
Oh.
But this doesn't happen in reality.
So why don't atoms collapse?
Well, quantum mechanics explains this by treating electrons not as these point-like particles, but as waves. These electron waves, they can only exist in certain stable states or orbitals around the nucleus. And each orbital has a specific energy level. And electrons can jump between these energy levels by absorbing or emitting photons of light.
So the stability of atoms is due to,
in large part, yes,
the wave nature of electrons.
That's a big part of it.
Wow.
And this has profound implications for our understanding of the world. It explains why atoms have unique spectral lines. You know, the specific colors of light that they emit when heated. It also underpins our understanding of chemistry and the behavior of molecules.
So this abstract concept of wave-particle duality, it has real-world consequences.
Absolutely. The wave nature of matter, it isn't just some theoretical curiosity. It has led to incredible technological advancements.
Like what?
Well, take electron microscopes, for example.
Oh, yeah. Electron microscopes.
Yeah.
Those are those super powerful microscopes that can see things at the atomic level, right?
That's right.
Okay.
Electron microscopes, they exploit this wave-like nature of electrons to achieve much higher resolutions than traditional light microscopes.
But how can they use electrons, which are particles, to create images?
Well, instead of using beams of light, electron microscopes, they use beams of electrons. And remember, electrons, they have a wavelength associated with them. And just like light waves can be focused and diffracted, electron waves can too.
That's cool.
So by focusing a beam of electrons onto a sample and detecting the scattered electrons, scientists can create incredibly detailed images of objects at the nanoscale.
So we're harnessing the quantum world
to
explore the universe
at
its tiniest scales.
Precisely. And there are many other technologies that rely on our understanding of wave-particle duality. Semiconductors, for instance, which are the foundation of modern electronics. Those are another great example.
So our smartphones, our computers, all these gadgets we rely on, they wouldn't exist.
It wouldn't be possible
without this quirky world of quantum mechanics.
That's a great way to put it.
Wow.
Our understanding of this dual nature of radiation and matter, it has really revolutionized the way we live and interact with the world.
It really has.
And there's still so much more to learn and discover in this field. In this field. Who knows what other amazing applications will unlock in the future?
Yeah, it's incredible how something as abstract as wave-particle duality has led to such tangible advancements. So far, we've delved into the theoretical frameworks that describe wave-particle duality. But is there any experimental evidence?
That's a good question.
To support these theories?
There is.
Really?
Did scientists actually observe matter behaving like waves? Yes, they did.
Wow.
One of the most famous experiments that demonstrated this wave nature of matter is the Davison-Germer experiment, which was conducted back in the 1920s.
All right, what did they do in this experiment?
Well, in the Davison-Germer experiment, they fired a beam of electrons at a nickel crystal. Now, if electrons were purely particles, you would just expect them to scatter randomly off the atoms in the crystal.
Like bouncing tiny marbles off a wall.
Exactly. But what Davison and Germer observed was something quite different. They saw a diffraction pattern.
A diffraction pattern.
Yeah, similar to what you see. When you shine light through a narrow slit or diffraction grating, the electrons were interfering with each other.
Interesting.
Creating these regions of high and low intensity.
Wait, so the electrons were acting like waves? Interfering with each other? Just like waves of light do?
Precisely.
Wow.
The regularly spaced atoms in the nickel crystal, they acted like a diffraction grating for the electron waves.
Got it.
And this diffraction pattern, it provided compelling evidence that electrons, which we previously thought of as particles, they also exhibit these wave-like properties.
So this wave-particle duality, it's not just a theoretical concept.
Yeah.
It's been experimentally verified.
Yes. The Davison-Germer experiment,
Oh.
along with many other experiments that followed,
Okay.
really confirmed this wave nature of matter.
That's pretty amazing.
Yeah, it's a fundamental aspect of how our universe works, especially at the atomic and subatomic scales.
So does this mean that everything in the universe is both a wave and a particle?
In a way, yes.
Okay.
It's more accurate to say that these classical concepts of wave and particle, which are based on our everyday macroscopic experience, they don't fully capture the nature of quantum objects, like electrons and photons.
Gotcha.
These quantum objects, they exhibit both wave-like and particle-like properties, depending on how we observe them.
That's pretty mind-boggling.
It is.
Our everyday intuition doesn't really prepare us
It doesn't.
for this strangeness of the quantum world.
It's true, the quantum world.
Yeah.
It operates under a different set of rules.
Okay.
And it really challenges our classical understanding of reality.
It does.
But even though it's strange and counterintuitive, it's also incredibly beautiful and profound.
I agree.
Yeah.
Well, this deep dive into the dual nature of radiation and matter has certainly expanded my understanding of physics.
I'm glad to hear that.
We started with mysterious cathode rays.
We did.
And ended up exploring the wave nature of electrons.
And
the foundations of quantum mechanics.
Yeah, it's been quite a journey.
It really has.
Through the quantum realm.
I have to say, this chapter from India's NCERT textbook has been a fantastic guide.
Great resource.
On this journey.
It is.
So thanks again to NCERT.
Absolutely.
For making this resource accessible to everyone.
It's been a pleasure discussing these fascinating concepts with you.
Likewise.
The dual nature of radiation and matter. It's really a reminder that the universe is full of wonder and mystery.
It really is.
And by embracing curiosity and a willingness to challenge our assumptions,
for sure,
we can continue to uncover its secrets.
Absolutely. Well, that's it for today's deep dive. Thanks for listening.